Problem 1. The switch in the circuit below has been in its present position for a long time. At time t equals 0, the switch is flipped. What is the current through and the voltage across the inductor at time t equals 5 milliseconds? Other information about this circuit: the voltage across the battery is 12 volts, the inductance is 6 henries, and the resistance is 2 kiloohms. Please pause the video and do the problem. So let's look at this circuit as it currently is now. When the switch is in this position, this battery might as well not even be there. It's not connected to anything, it goes to a dead end. Which means the only two things in the circuit are the resistor and the inductor. Because a long period of time has passed, we know that the voltage across the inductor is 0. And by Kirchhoff's voltage law, if the voltage across this inductor is 0, the voltage across this resistor is 0, which therefore means the current is 0. So after a long period of time with nothing driving it, there's nothing going on in the circuit. And then suddenly the switch is flipped. Now the switch is flipped, but an inductor still keeps its old current. So before the flip, the current in the inductor was 0 amps. After the flip, the current in the inductor is 0 amps. So we can say that the initial current in the inductor is 0. Now by Kirchhoff's current law, which says that the current going into and out of a node must add up to 0, the resistor and the inductor are connected by this node right here, which means if there's 0 current in the inductor, there's also 0 current in the resistor. By Ohm's law, if there's 0 current in the resistor, there's 0 voltage across the resistor. And then finally, we use one more Kirchhoff's voltage law to say that the total change in voltage across this entire loop must be 0. But recall this time the switch has been flipped, so we are including the battery, which means a rise of 12 volts. Nothing happens through that resistor because there's no current in it, which means there needs to be a drop of 12 volts across this inductor. So the initial voltage of the inductor is 12 volts. Now, after a long time has passed, the inductor has reached steady state. There's no voltage across the inductor, which means voltage across the inductor is 0. We can once again use Kirchhoff's voltage law to say that that means there must be a 12 volt drop in the resistor. The resistor follows Ohm's law, V equals IR, which means if there's a 12 volt drop in the resistor, we can say the current through the resistor is 6 milliamperes. And then Kirchhoff's current law once again, if there's 6 milliamperes going through the resistor, there's 6 milliamperes going through this inductor. So for the inductor, we know that its initial current is 0, and its initial voltage is 12 volts. Its final current is 6 milliamps, and its final voltage is 0. So starting with current, we know that it goes from 0 to 6 milliamps. So it is rising from 0, which means we use the formula that starts at 0 and rises up, this one right here. That gives us the current through the inductor as a function of time is equal to the final current in the inductor times 1 minus e to the negative t over tau. Let's get some numbers in there. Tau, the time constant, is the 6 henries of the inductance divided by the 2 kiloohms of the resistor. And remember, kilo means 1,000. So 6 henries divided by 2,000 ohms gives 0.003 seconds, or 3 milliseconds. So the time constant is 3 milliseconds. We also know from here that the final current in the inductor is 6 milliamps. So the formula plugging in those numbers is current as a function of time is equal to 6 milliamps times 1 minus e to the negative t over 3 milliseconds. Now the question asks for the current at time t equals 5 milliseconds. So we take this function, plug in 5 milliseconds for t, 6 milliamps times 1 minus e to the, now This is negative 5 milliseconds and 3 milliseconds. The milliseconds cancels, so that can just be e to the negative 5/3. So 6 milliamps times 1 minus e to the negative 5/3. Plug that into your calculator, and you should get 4.867 milliamps. The other question asked was, what is the voltage across the inductor? So the voltage across the inductor starts at 12 volts and ends at 0, which means we will use the falling or the decaying equation. More generally, V of t is equal to V of 0 times e to the negative t over tau. We already found that tau was 3 milliseconds. And from this, we saw that the initial voltage was 12 volts. So the formula is V of t is equal to 12 volts times e to the negative t over 3 milliseconds. Plug in the 5 milliseconds for t. The voltage at 5 milliseconds is 12 volts times e to the negative 5/3, or 2.267 volts. Question 2. In the problem above, when did the inductor have 2 milliamperes of current running through it? Please pause the video and do this problem. So the question asks, when is current equal to 2 milliamps? Well, we have our formula for current. The general formula is this. I of the current, or I of time, the current as a function of time, is equal to the final current times 1 minus e to the negative t over tau. So let's do a little bit of algebra. First, let's divide out the final current. So I of t over I final equals 1 minus e to the negative t over tau. Then we add this term to both sides and subtract this term from both sides. This gives us e to the negative t over tau equals 1 minus this ratio of the currents. Now the next thing we need to do is take the natural logarithm of both sides. Recall the natural logarithm is the inverse function of e to the x. So the natural logarithm of this side just becomes negative t over tau. And then this is natural logarithm of 1 minus I of t over I of f. Finally, multiply both sides by negative tau, and you'll get t by itself. So t is equal to negative tau times the natural logarithm of 1 minus the current ratios. At this point, plug them in. Tau is 3 milliseconds. The current at the time we're looking for is 2 milliamps. The final current is 6 milliamps. 2 milliamps over 6 milliamps is 1/3. 1 minus 1/3 becomes 2/3. And so the time is this negative 3 milliseconds times the natural logarithm of 2/3. ln of 2/3 is 0.4055. And so the current is 2 milliamps when time is 1.216 milliseconds.